it's a big honor to be here. In the next 25 minutes, I will talk about my research and my passion, high-resolution modeling. But I wanted to start off with a question to you. Since this is the Swiss Global Change Day, I wanted to ask you about your knowledge about Swiss climate. So let's jump in. How much is the annual average precipitation in Switzerland? So who thinks it's 700 millimeters, something like that? You can raise your hand. Not too many? 1.3 meters? Okay, quite a few. Who thinks 1.9? It's a little bit higher than I am, okay. 2.4? No, yeah, good job. It's actually B. You can see this here. It's 1,300 millimeters. Of course, there's a lot of variability. Some years are drier, some years are wetter, so this is the long-term average. And actually, fun fact, global climate models can simulate that quite well. There's a nice paper where I got this graphic from Esteban et al. 2025. And you can see, on average, like this multi-model mean of CMIP models gets 3.5 millimeters per day, which is approximately 1.3 meters a year, which is nice. But the question is really like, it's an odd number because it really doesn't represent precipitation well in Switzerland. Because if you look at what we really observe in Switzerland, you get this map. And you see massive variability of precipitation. This comes from ETHZ. And an interesting fact here is that one of the driest spots in Switzerland, it's in the Visp Valley, has approximately 543 millimeters. Very dry. These are these arid inner alpine valleys that we know quite well. If you go there, you can see this in the vegetation, that it's a very dry region. And only 25 kilometers away is one of the wettest spots in Switzerland, which has approximately 3 meters of rainfall, the Jungfrau Aretsch glacier region. Now you can think like if we have global climate models, you saw how big the grid cells were, approximately 100 kilometers. You cannot resolve these gradients at all. So you really need high resolution modeling for resolving these gradients. And most importantly, you can also see this topographic effect on precipitation in the climate change signal. So this is shown here, this is from the Swiss climate change report that we published last year. This is precipitation change in summertime at 3 degrees global warming, and you see some regions, in high mountain regions, have zero change, and other regions, which are very close by, have minus 30% of precipitation. So understanding how this looks like in the future, how our precipitation, how water resources are changing, is of high importance, and we really have to understand this by, I think, really high resolution modeling is one of the best ways to understand the processes that drive these changes and shape the current and the future water resources in Switzerland. You can really look at this and you already see what a topography is. So one big benefit of high resolution modeling is certainly how well we resolve topography. And I wanted to show you this animation just to show you how the topography of the Alps looks like in different models depending on their grid spacing. And we start off with something that was considered a high resolution model in CMIP6, this last generation of global climate modeling comparisons. Which is a proud 100 kilometer, and you can see like the Alpine rim looks pretty not so good, like it mostly is one grid cell wide. The highest peaks are somewhere in Italy, Austria, where they should be actually in France or here in Switzerland. And you can also see the coastline looks really not great either. Corsica is not an island, you could just drive there. If we see how the grid spacing changes if we go to high resolution, we start somewhere at 80 kilometers. This is the grid spacing that the German Met Service will use in their CMIP7 simulations. It's the atmospheric grid spacing. So it's certainly better. Now Corsica is actually an island and we have a little bit better topography, but far away from anything that would resolve alpine valleys and give us local scale information about precipitation, for instance, and how it changes into the future. What we can also look at is regional modeling. So we have coordinated regional climate modeling experiments that are shown here, the Codex project. They're running currently a 12-kilometer grid spacing, and you can see now it's certainly a better representation of topography and coastlines, but still, you can also see this in the precipitation map here we miss lots of the details. So that's why numerical weather forecasting, so for instance ETHZ, but also we in our group, we really like to push the grid spacing of these models to higher and higher resolutions, and we are typically operating at kilometer scales, and this is the grid spacing that we currently use in our setup for climate modeling. I can show you this again. I think the best way to see how the topography looks like, you probably have to look from above. This is basically what I'm showing you here, and there you can see this 2 kilometer grid spacing. It's also what ETHZ is partly using for their forecasting. You can really look deep into the valleys, like this is not a Rhone Valley and the Visp Valley. And you see these green colors, like very low valleys, close to very high peaks. So we really start to resolve these topography effects. But topography is only one part of what we improve when we go to higher grid spacings. It's also atmospheric dynamics. This was actually one of the first simulations that I did when I was a PhD student, back then with the Cosmo model. You can see how small the domain here is, like we could afford 3 months on this very small region over the Eastern Alps in Austria. What I'm showing you here is how precipitation looks like during a typical summer day in the observations, which are on the right, a 10-kilometer version of the Cosmo model in the middle, and then a 3-kilometer version on the left. And you can see, if we let this start from the beginning, if we focus on the observations first, you see at midnight there's no rain, nothing. The morning is clear. Until noon there's no rainfall, and then these very heavy pockets of heavy rainfall are popping up. These are the thunderstorms that we all experience in summertime in the afternoon. If you look at the 10-kilometer simulations, it starts to rain way too early. It's very widespread, low intensity, so it really doesn't resemble anything that we see in observations. But if you go to 3 kilometers on the left side, it's really a regime shift. Now you see you get this very heavy rainfall, the structure of the systems looks roughly correct, the timing is much better. This has been confirmed again and again with multiple studies. That's a very robust benefit of going to kilometer scale grid spacings, that you start to resolve thunderstorm dynamics way more accurately. That's a nice paper, like 10 years after what we did in 2013. Now we have kilometer scale climate modeling in ensembles over the Alpine region, performed in Codex as well. And what we are looking at here now is again heavy summertime hourly precipitation rates. And the left side is showing the observations, so you can see quite heavy rainfall. This is the 99.9 percentile of hourly rainfall in summer. And then if you compare this to what we get from a 12-kilometer model, this is the typical Codex resolution that we have also nowadays. You're almost an order of magnitude too low with the intensity of rainfall. So it's this typical bias, you have too little intensity and too high frequency. But if you go to the 3-kilometer simulations, you get a much better representation of what we observe. And this is now really robust because these are multiple ensembles run over 10 years. So we can be very confident in this benefit. And of course, this can't be translated into impact modeling. If you think about flooding in alpine catchments, you really want to resolve better represent heavy hourly rainfall in your models. So the reason why this is happening is basically the way we simulate deep convective clouds. If you think about a typical climate model that we use in CMAP, for instance, you have a whole population of clouds within one grid cell. Like if you assume the grid cell is 100 kilometers, you have to parameterize the clouds. So you have to basically use a statistical model that's connected to some variables that are resolved on your grid to estimate what the clouds would do within the grid cell. If we increase the grid spacing, so this is approximately 25 kilometers where high-resolution global models are running today, we still have to use this parameterization, but approximately at kilometer scales, 4 kilometers, 3 kilometers, if you have a model that has high accurate numerics, that is really designed to do mesoscale simulations, you can really turn off this parameterization and can the model let the model simulate explicitly the deep convection. That gives us this big benefit. There's another example just to illustrate how these clouds look like in these two worlds, where we have 12-kilometer parameterized convection on the left and the 4-kilometer on the right. This is actually an organized convective storm, so you can see this on the right. We have multiple updrafts, this bubbles rising. We have also this cold pool that you see at the bottom that we know from our experience. If you see a thunderstorm coming towards you, you often feel this cold gust of wind. that's approaching you. This is very nicely shown. These cold pools are triggering new updrafts, and there's really a regime shift between what we can simulate on the left side and the right side. But that's why, again, numerical weather forecasting centers are really pushing towards this high-resolution kilometer scale modeling, and this is also why we want to use these kind of models in our climate change assessments. So now you can ask, why wouldn't everybody use these models at kilometer scales? But of course, these models come at a cost, and it's the high computational costs that really limit the application of these models. And I wanted to give you just a couple of numbers to illustrate how big the difference in computational costs is compared to a typical CMIP model, comparing those to a kilometer scale global model. So these were simulations that we ran on the same supercomputer called Cheyenne with different modeling systems. This is what 1 year of CSM, the Community Earth System Model 2. This was the contribution of NCAR to the CMIP 6 archive. This is their flagship configuration costs. It's 3.45 thousand CPU hours per year. You don't have to worry about what this means. It's just a number to give you a reference. But this is what the costs are if you increase the model complexity. This model, this vacuum configuration, has model chemistry included, and there's a very high top, so you can do stratospheric processes way better. It has an order of magnitude more cost. So now we are 22,000 core hours per year. We did simulations with the Weather Research and Forecasting model, which is similar to Cosmo or ICANN. It's a regional model at 4 kilometers, but only over a regional domain. So this was over the North American continent, approximately 5% of the globe. Now we have another order of magnitude more costs per year. Now we are at 420,000 core hours per year. And then finally, we did a simulation with the AMPAS model, the model for prediction across scale, which is similar to ICANN. It's a global setup at 3.75 kilometers, and there we had 24 million core hours per year. So you can really see how expensive it gets as you increase the grid spacing. Just to put this into context, if you have the same computational resources, how long could you run each of these models? And if you have the resources to run 2 years of this AMPAS simulation globally, you could run 13,000 years with the CSM2 configuration that was used in CMIP 6. This would bring you back to the early dryas. This is when we had the last cold period where humans were hunting mammoths. If you use the same computational resources for AMPAS, it would bring you back 2 years. This is the end of the era to by Taylor Swift. So just to illustrate, it's very different questions that you can ask from these models, depending on if you can look at 13,000 years or 2 years. So that's also the reason why these kilometer scale models were so far quite limited in their reach. In a coordinated fashion, in this Codex project, you can see the domains that coordinated experiments were run with multiple of these kilometer scale models. In the red boxes, you can see the boxes are quite small. The largest ones are maybe continental scale, but maybe often smaller. The longest simulations are 10 years or so because it's so expensive to run them. This has two problems. The first one being, you can also see where the location of these boxes is. It's mostly in Western countries where we have a lot of resources, but it's not in countries often where you have the highest impacts of climate change, in the global south. And secondly, any benefit that you would get out of high-resolution modeling, like if you resolve the Alps much better, doesn't really propagate to any other region. It stays in this very limited area. So you really confine yourself. And you also depend on the quality of your lateral boundary conditions. So anything that you use to drive the regional models, you really have to believe that these models give you the right lateral boundaries. And often they don't. So this is a nice study here that shows systematic biases in our global climate models, specifically for blocking. And you can see from CMIP 3 to CMIP 6, we have quite consistent biases in underestimating the frequency of blocking. Blocking means that weather patterns don't move westward anymore in mid-latitudes. And we see this quite consistently, so we have two zonal jets, the blocking frequency is too low, and the ridging, the meandering of the jet stream is not well simulated. The problem is these weather patterns that have very meandering jet streams can have a really big impact. Like one nice of these patterns that we had just 2 years ago is shown here. This was the 5th of September 2023. This is called an omega block, for those of you who know that. Like, it looks like an omega. What you have is basically a heat wave over Central Europe, and then you have 2 low pressure systems on each side of this block that basically caused flooding simultaneously in Spain and Greece, whereas at the same time people in the UK went to the beach because it was so hot. In Bern it was 29 degrees Celsius, so way warmer than the climatology for early September. The storm that we see on the right-hand side in Greece, it moved over the Mediterranean and hit a few days afterwards Libya, and you probably remember the Libyan floods where these dams collapsed and killed more than 1,000 people. So simulating these weather events in our climate models is extremely important because they can lead to very high impact weather. And one of the hopes is really that the high-resolution models can give us a better representation of this blocking and this wave amplifications that we see. It's a very exciting area, at least time for me at least, but I think for the whole climate community, because we are really now in a situation where we can run kilometer scale models globally, which means we can simulate each and every single storm on a global scale and how it interacts with the climate system. What I'm showing you here is a screenshot of a simulation that we did with the ICON model. We have a big project at ETH called Exclaim, where we modernized the code of ICON to efficiently run on the ALP supercomputer at CSCS, which is one of the biggest supercomputers on the Earth, using GPUs. It's a very efficient setup. And we're now able to run this configuration at 2.5 kilometers globally. And we have done this for 4 years as a demonstration here. And I wanted to show you how this simulation looks like. But what we're looking at here is the August of 2020. And we're zooming into Africa. This is the season when we have the North African monsoon. You can see all these big cloud fields, these mesoscale convective systems, they evolve on the Dell cycle and they move westwards with the flow. I wanted to stop maybe quickly here and show you, like here, like there was a massive outbreak of MCSs along the coast. And this cloud cluster is actually moving westward and interacting with an African easterly wave, which is a tropical wave that moves globally around the globe. And this interaction between the mesoscale convective systems and these global waves is triggering a hurricane, as you will see in a second. So we can follow this. You can already see how the clouds start to rotate. And now we have cyclogenesis, and this cyclone grows in intensity and strength, and eventually hits the east coast of the United States as a major hurricane, then makes extratropical transition, stays a little bit there, then gets wrapped up in the westerly flow of the mid-latitudes. I think it's a beautiful demonstration of how weather and climate on a global scale are connected. So whatever happens in Africa can have a big impact, of course, on the US, but eventually also in Europe. So climate and weather you cannot put in shoeboxes. You really have to think about how these things connect, and even thunderstorms can have a big impact on downstream weather events. Just a few nice results from this 4-year-long simulation. What I'm showing you here is the maximum hourly rain rate at each grid cell in this 4-year-long period. What you can nicely see the tracks of each hurricane that we simulate. So the hurricane tracks look very realistic in this simulation. You can also see extratropical cyclones, all the streams in the mid-latitudes over the continents, especially the US, for instance, but also other continents, Africa. You can see this streaks of high rainfall. These are thunderstorms that move over the country that produce very heavy rainfall. We know that this is realistic from radar observations, but you really can only simulate that once you go to kilometer scale model resolution. We compared the output to station data and also satellite data. This is shown here. This is just for Western Europe, but the quality of how we simulate the probability density distribution of hourly rainfall is extremely good in these simulations. It's even outperforming our satellite observation capabilities compared to ground stations. This is the same picture, but now for wind gusts. And here the cyclones are even more pronounced, so you can really see where the cyclones are going. But again, you can see also the extratropical cyclones. You can see again the streaks over Africa. So for instance here you can see this mesoscale convective systems moving out over Africa, over the Atlantic, and eventually sometimes triggering cyclones. You see these streaks in North America, you see topographic enhancement and so on. Again, compared to observations, the model does a really good job in capturing these wind gusts as well. So we're really happy with these simulations, but I haven't talked about really this upscaling a lot, like what now, like if we can simulate the large scale weather or synoptic scale weather better with these high resolution models. So we working on this in a PhD thesis. Marius Rixen, who is here today, is a very talented PhD student in my group, is working on this topic. He's looking at 3 case studies. This is one of them that I wanted to show you. This is Storm Dennis. Storm Dennis was one of the strongest extratropical cyclones in history that we observed over the North Atlantic, happened in 2020. And it was related actually to a mesoscale convective system, so an outbreak of convection over the US. What I'm showing you here is this, where we start the simulation, so this is more like a forecast. You see over the US, you have this mesoscale convective systems that really perturbs the wave, the jet stream downstream. And we picked this case because the global weather forecast from ECMWF with the IFS model had a forecast bust, which means this weather pattern, this storm was very poorly forecasted by the global forecast system. But it had a really big impact on the UK, so it brought major flooding, coastal flooding, inland flooding to the United Kingdom. So again, forecasting these weather patterns, these storms, realistically is of high importance for society. So we try to understand if we can forecast this system better compared to what the IFS forecast did. And you can see basically here, you can see what really happened. This is approximately where jet stream is and what IFS did. So it really misplaced the storm way too far to the east, to the west. So in our simulation, like we looked first on this representation of this MCS in the central US, very heavy rainfall. You can see, depending on the model grid spacing, we have a way better simulation of the heavy rainfall that was occurring there compared to the 40 kilometers, which is the purple run. Has very low heavy rainfall, and the 4 and the 5 kilometer, 2.5 kilometer simulations are very close to observations. And this really translates in how well you can forecast the storm. And this is shown here in this anomaly correlation coefficient. The higher, the better. And you can see we start off, this was the forecast bust, so quite low skill scores. 40 kilometers really doesn't do a good job. Like with 40 kilometer model, you cannot simulate this situation very well, but you can see if you go to 20, you get a good improvement. 10 kilometers is actually outperforming the IFS model, and then starting with 5 and 2.5 kilometers, we much better simulate this cyclone compared to traditional weather forecasts. So very promising results, and we're trying to generalize this now and see if we can really leverage this for climate change simulations. So wrapping up, I think we are really entering a new era of climate modeling capabilities. I'm very excited about the kilometer scale models. It really allows us to look at mesoscale processes and their role in the climate system, and also how they affect larger scale circulation, not only local scale extremes, for instance. I also want to emphasize this is not a silver bullet. So just increasing the model grid spacing is not enough. You really have to heavily invest in model development. Things get you have to rebalance the model and often work on parameterization schemes, include new parameterizations. And there's still, like these models will not replace coarser resolution models anytime soon. So the coarser resolution models will have an important place to play here. But it's really, I think, these modeling systems have complementary weaknesses and strengths. So we really should work together to better understand how climate change is changing in the future. And I'm pretty sure that this will help us to get to more actionable climate change information in the future. Just to say, we already heard a little bit about this NCCR Clim Plus project. We will use this modeling framework, ICON and high resolution modeling heavily there to really improve our understanding of climate change in Switzerland and build up resilience in Switzerland. So I'm very excited about that. I'm involved in also building up this climate and weather platform, which is a computational platform that will give access to the data sets, but also the computation and the analysis to the whole Swiss community. So if you're interested to work with the data sets, you really please reach out, let us know. And the idea is really to basically open up the data as soon as possible and also find new ways to interact with the data, for instance, with generative AI. If you're generally interested in this topic, I also wanted to give a brief shout out to this workshop on climate risks in September in a very beautiful location, Spain. Shahan, I think, is here if you have any more questions. The QR code is there if you want to screen it and look at the program. And with that, I want to thank you for your attention and looking forward to some questions. Thank you.